Hello students, in this video we'll discuss the determinant of powers, inverses, and transposes. Here's our first proposition. The determinant of A transpose is equal to the determinant of A. Okay, and how do we prove something like this? Well, we use our standard trick of saying we know proof if E is an exchange matrix, then E transpose is equal to E inverse, right? And so in this case, determinant of E is determinant of E transpose. So in other words, this proposition is true for exchange matrices. If F is a scale matrix, scales rho I by lambda, then if I transpose this, it's itself transpose, right? Then F is equal to F transpose, and therefore determinant of F is determinant of F transpose. So in other words, this result is true for scale matrices. And finally, if G adds a multiple of one row to another, then so does G transpose. Determinant of G is determinant of G transpose. In other words, this result is true for all elementary matrices. So in other words, this is true for all elementary matrices. All elementary matrices. Great. And so now two things can happen. So case one, A not invertible. Then we know determinant of A has to be equal to 0. If A is not invertible, neither is A transpose. A transpose not invertible either. And so the determinant of A transpose is also equal to 0. So in the case when A is not invertible, determinant of A is equal to 0, and that's equal to the determinant of A transpose. And so this is true in the case when A is not invertible. If A is invertible, case 2, A invertible, that means that A is the product of elementary matrices. These are elementary. And what we can do now is we can use the power. We can say that the determinant of A is going to be the product of these determinants, determinant of E1 all the way down to determinant of EK by a previous video. But a transpose is just going to be these things in opposite order. It's just going to be EK transpose all the way down to E1 transpose. And that says the determinant of A transpose is going to be the determinant of EK transpose all the way down to the determinant of E1 transpose. But those two expressions are equal because it's true for elementary matrices, so the determinant of A transpose is equal to the determinant of A, and so we have the proof of our proposition in this case. So this is a very, very useful result. The next two propositions are relatively straightforward. They just follow from the same sort of product theorem, right? So the determinant of A inverse, if it exists, of course, is 1 over the determinant of A. And the proof of this is elementary. It's just that A times A inverse, if it exists, is the identity. So by taking determinant of both sides, I have determinant of A times determinant of A inverse. By our power properties for that is the determinant of the identity, and the determinant of the identity is a diagonal matrix that's just equal to 1. So therefore, this determinant of A inverse is 1 over the determinant of A. That proves that proposition. And now also, just by induction, so we have transposes, inverses, and now powers. If I do the determinant of A to the power n, trivially, what can I do? I can say this is really just the determinant of A to the power of n, right? Now, it bears warning that these results are true for powers and inverses and transposes, but they're not true for some. So in general, it can be the case, if we think of a simple example like this, if I say, okay, well, this thing over here has determinant 1, right? But if we add to it if we add different things to the identity, we can see that the rules for sums are not true. So in general, it's not the case that the determinants, we can just clear that out. So in general, note, determinant of A plus B is not equal to, in general, determinant of A plus determinant of B. So there's no sum rules for determinants, but in special cases you can get results that are similar to this, which you'll see in further videos. Thank you very much.